Hello friends, so today we are going to solve 4 questions from rotational motion, and one second, let me check whether it is working properly or not, otherwise it always gives the problem. Okay, I think it's working. Okay, so in the first question we are given that we have a car and that car is weighing close to, so car of mass 1600 kg has its center of mass located midway between the front and rear wheel and 0.7 meter above the ground. The distance between the front and the rear wheel is 2.6 meters. Okay, so we are given the distance between the front as well as our rear wheel that is given to us. And along with this, we can based on this, we have 2 questions. First question is, find the minimum acceleration A required for the front wheel to just lift off of the ground. Part B, if the car decelerates at a rate equal to g, determine the normal force acting on the front and the rear wheel. Okay. So let us draw an approximate figure, and we are given that we have a car which is moving with the acceleration of our A. So let us suppose this is our ground and we have a rear wheel of the car and this is our front wheel of the car, and we can just draw the car something like this. Okay, so this completes the car and it is moving towards the right side with the acceleration of A, and let us suppose there will be, you can say, 2 normal, and we are going to have normal in the rear wheel, normal in the front wheel. Okay. And let us suppose L is the total length of the car, and obviously there will be mg, and it is said in the question itself it is exactly at the center. So we assume that the distance from the front is to the center of mass is over x, therefore from the rear it will be coming as L minus x. So this is our basic question for the first part. Okay. And let the height of this, you can say, the center of mass from the ground is suppose our h. And so we are going to solve this question into 2 ways. First, we are going to consider the non-inertial frame, and then we are going to consider a inertial frame. Okay. So let us start with our method 1, and in this method 1 we are going to consider non-inertial frame. Non-inertial frame, or we can also call it as a accelerating frame. Accelerating frame. So obviously there will be a pseudo force that will be acting on it, and the pseudo force will be acting in the opposite direction of motion and along the center of mass. Okay. So let us call this as F in. So this is a pseudo force, and its value will be equal to minus m times A. A is the capital, so we can just put it capital A. So we can write that the pseudo force that is F in will be equal to minus m times A, and it will be acting at our center of mass and in the direction opposite to the acceleration. Okay. And so we are interested in first case that the front wheel is going to lift off. So whenever there is a lift off condition, so obviously we are talking about the normal, because as soon as there is a lift off, that particular normal will be equal to 0. So if we are talking about the lift off at the front wheel, so this NF should be equal to 0. Therefore, we do not require this our rear wheel. So we are going to take the moment about this rear wheel. Okay. So only the moment about the front will be in the picture along with these two forces. One is pseudo force and other one is our mg. So you can say taking moments about rear wheel and first one will be our the inertial force, that will be our ma times h. So we have our from inertial force, okay, or we can say lifting from the front. Lifting from front. And this inertial force will be our ma multiplied by h, and it is going to have a positive sign. Okay, positive, which is going to try to lift the car, and negative when it is going to keep the car down. And the second one will be the from the weight, and this weight will try to keep the front down, keeping the front down. Obviously that will be opposite for our negative, that is mg times x, and the other one will be the front normal about the rear. So we have from front normal, that is our NF about the rear. And that will be equal to plus NF multiplied by L. And everything should be in equilibrium. Okay, then we can later on substitute that normal is equal to 0. Therefore, we can say for equilibrium, we can write that our NF times L plus we have our MA times H minus mg times x is equal to 0. One second. Oh, here I have taken this. So this is our x and this is our L minus x. Okay. Because we are taking the moment about the rear wheel. And we are going to put now NF is equal to 0. So we can say our part A gives us that front just lifts and therefore NF will be equal to 0. And if NF is equal to 0, this will be equal to 0. So we are left with only 2. We get this as our, this is capital, not small. And here also. Therefore, we can say that our NF will be equal to 0, which gives us that the summation of MAH minus MGX is equal to 0. So obviously M cannot be equal to 0. So we can just remove it from here, and this gives us that value of our acceleration, that is our A will be equal to, we have our G times X divided by H. We simply substitute their values. This is 9.8 times X, and X is exactly the midpoint, that is 1.3, and height is given as 0.7. So we get the acceleration will be approximately equal to 1.8 we can say 18. .20 meter per second square. So this is our acceleration. And for part B, it states that the car decelerates at a rate which is equal to g. Therefore, we can say for our part B, we are having a deceleration is of our, let us suppose this is deceleration is of minus g. Okay. Minus g. Or we can say this will be our equal to our A, because we can just substitute it. Therefore, we can put it in this equation. We have our NF times L. This will be coming as minus MGH minus MGX. Is equal to 0. And therefore, we get our NF will be equal to we can take mg as common, and this comes as h plus x and divided by L. Now we simply substitute the value. We get NF. M is given to us as 1600 multiplied by 9.8, and height is given to us as 1. Height is 0.7 plus 1.3, and length is given to us as 2.6. So this NF will be coming close to as our 120 and 61 newtons. Okay. And for our rear wheel, we can just say that taking the forces in the vertical direction, so we have two forces in the upward direction. One is the normal at the rear wheel, and the front wheel in the downward direction we have our mg, and everything is in equilibrium. Okay, so if it is that is equilibrium, their summation should be equal to 0. So we can say that for equilibrium, let us say we have our x-axis and this is our y-axis. So we can say summation of forces in y-axis should be equal to 0. And under this condition, we can write that our rear wheel plus front wheel should be equal to our mg. From here we can say our rear wheel will be equal to our mg minus front wheel, and our mg is equal to 1600 multiplied by 9.8, and front we already calculated is 12061. Therefore we get that the normal at the rear wheel will be approximately equal to 316 Newton. And this we solved using our you can say the non-inertial frame. We can also solve this same question by using the inertial frame. In that case, we are going to take moments about the front wheel, and similarly we can just make adjustment for the torque. So we have this as method 2. And in this method 2, we are going to discuss the inertial frame. And once again, for tipping point, we know the normal should be equal to 0. So obviously, the NF will be equal to 0 because the tipping is along the front part. Okay. Therefore, we can say that moments about the front wheel and once again we are going to take positive when there is a lift off, and when there is a move downward we are going to take as negative like we take in the first part. So the first force is obviously our mg. So force is our mg, and it is acting at a distance of L minus x from the front. Okay. So we have our mg at a distance L minus x from front. And next force is our center of mass, and we can say, sorry, center of mass we just took as mg. Other one will be our the net inertial effect, which is our pseudo force that is acting at a height of h, perpendicular distance h, and its force magnitude is m times a. Okay. So we have our horizontal net inertial force and acts at center of mass at a height, and that height is our h. Therefore so we have our mg L minus x and we have our mgh. Okay. So this will be giving us plus mah because it will be moving the car in the downward direction, and this will be giving us minus mg L minus x. And likewise nf should be equal to 0. Therefore for equilibrium the summation of the moment should be equal to 0. So we have over here plus mah minus mg L minus x is equal to 0. And now it is quite simple. We are only interested in finding out value. Okay, here also this should be capital, not small. Okay. This is our capital, and therefore we can write that our acceleration A once again will be coming as gx times h, and the answer will be coming as same, 18.20 meter per second square. And for normal, the you can say the concept will be entirely same. Okay. And we can write that our front normal will be equal to our mg x plus h upon L. I think that was, yeah, so it was mg h plus x, and obviously the answer will be coming as 12061. And for our rear, we are going to take the algebraic sum along the y-axis, and the rear will be coming as 36.18. 36.18 Newton. Okay, same question we can solve by using the inertial as well as non-inertial concept. Okay. And in this case, the normals are to be found out for part B. Okay. So this solution is for our part B. Okay, part B not going to change, only the part A solution, yeah, method approach is going to change. Come to next question. It states that a top of mass m spins with the angular speed omega s about its axis. The moment of inertia of the top about its spin axis is I naught, and its center of mass is at a distance L from the pivot point. The axis of the top is inclined at an angle of phi with respect to the vertical, and the top undergoes uniform precession. Gravity acts downward. The top is an elevator, is in an elevator with its tip held to the elevator floor by a frictionless pivot. Find the rate of precession omega, clearly indicating its direction in the following cases. So we have two cases. In both the cases we have to find out this precision, that is omega, along with its direction. First is that elevator is at rest. Part B, the elevator accelerated downwards at a rate of twice g. So first let us draw the approximate figure and then we can just follow from there. So we are given that there is a lift suppose we are going to draw it open lift, much more easy to picturize or visualize, and it is the the pivot point is okay. So we can just draw a you can say top, and let us suppose this is the pivot point, okay, at one of the ends, and let us draw this is the axis, and the top will be something like this. So this is the top. And this top is at an angle of phi with the vertical. So let us suppose this is the vertical axis and this angle is given as to us as phi. And it states that it has a spin angular speed, that is Ws, and it is rotating in this direction with a spin angular speed of Ws. Moment of inertia is given to us Is, and the rate of precession, that is omega. So the omega will be around this vertical axis, and we are going to find out its direction for two cases. Okay, so here I am not going to draw the direction, but it will be along this vertical axis. That's the only thing here. And we are also given that its center of mass is at a distance of L. So let us suppose the center of mass is somewhere here, and we have our mg in the downward direction, and it is at a distance L from the pivot point. And yeah, and moment of inertia is given as I naught. Okay, so these are the things which are given to us. So okay, and along with this there will be also normal that will be acting at this pivot point, which is not required in this case, but still we can just draw it. Okay, so this will be normal that will be acting in the this pivot point. And obviously there will be along with this, so we can say there are total three forces. One will be mg, another one will be normal, and there will be also a horizontal force at the pivot point, which is going to provide the necessary centripetal force for the precision, because it is going to if I draw it here, so this is our horizontal vertical axis, and if we assume that the top is nothing but a single rod, now this rod is going to rotate, or rather we can say revolve around this axis. Okay, so there will be also a, and this is said to be given as our omega, and its direction we don't know. For the time being I am just assuming that it's moving in this direction. Okay, so first of all we are going to make a complete discussion about this in a elevator's non-inertial frame. Okay. So we are going to discuss it is in the elevator's non-inertial frame. Entire discussion will be carried out in this part. So let us assume that here we take G as G effective, okay, because it is an elevator. No doubt sometimes the elevator is at rest and at the time it is moving with the 2G, but we are going to take that as G is equal to our G effective. Okay, so later on we can just replace this our G effective anyways for the part A as well as part B. So let us consider that we are having the effective gravitational acceleration, or we can say effective acceleration due to gravity. So we can say effective gravitational acceleration, and let us call this as our G effective. Okay, and it is at center of mass. So we have a vertical force, like I said, that is a normal, but we are not interested in that. We are interested in, first of all, we can say that our torque that will be produced by this G effective. So we can say G effective provides torque and let us call this as our tau, and tau will be equal to m times G effective multiplied by our L, because L is the distance of this center of mass. And from here we can say that the torque is perpendicular to our G effective and is perpendicular to our length L. This we are going to use later on also. And we are given that there is a steady precision of rate omega. So we can say that for steady precision rate, which is omega, the rate of change of our angular momentum, that is Ls, should be equal to this torque. So for steady precision rate, the rate of change of spin angular momentum and that spin angular momentum is, let us suppose we had taken as Ls, and this Ls will be equal to our I naught multiplied by spin angular velocity, and it will be along the symmetric axis. And the spin angular momentum is equal to the torque, and this torque is equal to our the precision rate and multiply by our Ls, and this is our sine of phi. And now we can find out the torque due to our G effective. Okay, so for that let us and we have our this is our G effective, and vertical the angle is given as phi, so this angle will be also phi, and G effective we can take two parts. First one will be our G effective sine of phi, and this will be our G effective cos of phi, and this G effective cos of phi is along our axis, so it is not going to contribute to any of the torque, and this distance is given to us as L. So only this G effective sine of phi will be the part of that G effective which will be contributing to the torque. Therefore we can say that the torque magnitude and let us suppose that is our tau, and this tau will be equal to our m times G effective and sine of phi multiplied by the perpendicular distance. Okay. And we can also find out our rate of change of this spin angular momentum. Rate of change of spin angular momentum, that is Ls, can be written as our dLs upon dt, and that will be equal to our because Ls we just found out is our I naught times omega. Okay. And rate of change of Ls will be equal to our this one. So this comes as our omega, and Ls is our I naught omega s, and we have this as a sine of phi, which is nothing but our torque. Okay. And therefore we can just equate them, and for Ls we can also draw this figure, because we know that our spin angular momentum, that is Ls, is along the axis, and we are having this angle is of phi, and this is our omega, that is precision rate, and this precision rate we can divide into two components. One will be along the Ls, which will be our omega cos of phi, and other one will be the perpendicular part, that is our omega sine of phi. So obviously the torque will be only because of this perpendicular part. Okay. So cos phi is not part of that torque generated, and we can just equate this torque. So we can say that our equating we get our m G effective and mg effective sine of phi, mg effective sine of phi times L is equal to, and this comes as our omega I naught omega s sine of phi. And from here this sine phi goes away and rest is same. Therefore we can say that our precision, that is omega, will be equal to we have this as m l g effective divided by I naught times omega s. Okay, so we got the value of our this omega, that is the precision part. Okay. Now, like I said, that now we have to find out this direction of this precision part. Magnitude we got, and we are going to find out its direction. And in order to find out the direction, we know that our, like I said, the torque is perpendicular to our g effective as well as the length L, and also our spin angular that is velocity omega s is along the axis itself. It's not going to change. Therefore, the torque is going to increase the tilt. Okay, the torque is going to increase the tilt. Tilt means the angle. So this torque will try to increase this tilt. Okay. And to counteract this, in order to balance out, our precision, that is omega, must be such that the direction is opposite to the tilt in this direction. Therefore, we get that this omega will be in the in the clockwise direction. So this is our direction of omega. So this was our first part, and in the second part we can just say that in the part A it says that the elevator is at rest. So we have our elevator is at rest. And if elevator is at rest, and in the you can say lab frame, our g effective will be now equal to our g. So in the lab frame, g effective will be equal to our g. Therefore, we can simply use the given equation which we have solved it. We get that omega is equal to m times L g upon I naught times omega s. So this is our part A. Okay, and it will be clockwise when viewed from the top. Okay, so we have to remember this is clockwise viewed from top. Okay. And now we come to the part B. Part B states that our elevator accelerating downward at a rate of 2g. So we have elevator accelerating downward at rate 2 times g. So in this case, we are going to find out how the acceleration due to gravity is going to change. And so the elevator is moving downward with 2g, or from here we can say that the elevator's acceleration let us call this as A elevator, which will be equal to minus 2 times g. Okay. And there will be, in the elevator frame, there will be a force, or we can say a pseudo force, acting on the center of mass. Okay. Therefore we can say that in the elevator frame, pseudo force at center of mass, and let us call this as Fp. Then this Fp will be equal to minus of m times acceleration of our elevator. We substitute the acceleration of elevator and we get this as our plus 2mg. Therefore, the net force on center of mass, you can say that our net force on the center of mass, and let us call this as F effective. And this F effective, okay, here I forgot to mention that the actual, or we can say the true gravity, okay, it's a little bit difficult to assert the name, but for the time being we can just call it as a true gravity force. Okay, we can call this as true gravity force, and that will be equal to over minus times m times g in the downward direction. Now we can find out our F effective, which will be our pseudo force and our this true gravity force. Okay. So we are going to get this as our plus 2 times mg minus mg, giving us plus mg. Therefore, we can say that our G effective will be equal to our force effective divided by its mass, and this comes as a plus m times g divided by m. Here m goes with m, so this will be coming as our g or plus g, so it will be acting in the upward direction. So once again, our this precision, that's omega, will be equal to mgl, because G effective is equal to over G, and here also the G effective was equal to G, so nothing is going to change. So we had mgl upon I not omega s. So the magnitude is going to remain same. Only thing that is going to change is our direction. Okay. Because now the gravity is of a plus upward direction, therefore the precision rate, or we can say precision, which will be along the vertical, will be along the counterclockwise direction. So this will be direction of our precision. Okay. So the direction will be counterclockwise. So this is the major difference between the two. Magnitude is our same. Next question. It states that a pendulum is rigidly attached to an axle held by two supports, allowing it to swing only in the plane perpendicular to the axle. The pendulum consists of a mass m attached to the massless rod of length L. The supports are mounted on a platform that rotates with a constant angular velocity omega. Determine the frequency of the pendulum, assuming the amplitude of the oscillation is very small. So in this case, we can just draw an approximate figure. So we are having a platform that is being rotated at a constant angular speed of omega. So we can just draw a platform. So let us suppose this is our platform, and we have our, this is the axis of the platform, and it is rotating, suppose in this direction, with a constant angular velocity omega. And on this platform we have two pillars, something like this, and on this pillar we have a horizontal rod, and to this horizontal rod we pendulum is connected. Okay, let me draw it this way, and this mass is of m and the length is of l. So this is our basic figure, and for the sake of convenience we are only going to draw the rod as well as the pendulum, because rest thing doesn't matter. So this is a rod, and we are having the axis of rotation, and this is our omega, and this is our pendulum. Okay, so we have mass m and length is our l, and suppose the angle is a small angle, and that angle is our theta. Okay, so these are the things which are given to us. So here we are going to consider that the reference frame is a non-inertial frame. Okay, and so we can say that the rotating frame of the platform is considered as the reference frame. So we consider that rotating frame of platform as non-inertial frame, and therefore there will be a centrifugal pseudo force, because it will be try to rotate inside within a circle. Okay. So therefore we can say that we are having that in this frame the pendulum feels a centrifugal pseudo force. And in addition to gravity, gravity will be always there, and we can say centrifugal pseudo force in addition to gravity. Or we can say, we can consider two forces here. One will be a centrifugal pseudo force, and other one will be the force due to gravity. So first of all, and let us try to find out the first part, that is pseudo force. For that we require the centrifugal acceleration, and we say that our centrifugal acceleration, and if we assume that the distance from the axis of rotation is our r. So suppose this is a distance from the axis of acceleration, that is our r. So we can say at a distance r from the axis of rotation, therefore we can write that our centrifugal acceleration let us call this as A cent will be equal to our omega square times r, and it will be directed radially towards the axis, radially outward from the axis. Okay. And we can say that directed radially outward from the axis. And now we come to the torque about the pivot point. Torque about the pivot, and like I said that there is a small angle theta, so there will be we are going to have our mg in the downward direction, and so there will be a restoring force, and we are going to have, one second, so this angle will be over theta, and this angle will be also over theta. Sorry. So we have our mg, and we can find out the torque due to our this is going to have mg, this will be over L sine of theta. So the torque because of this mg will be equal to mg times L sine of theta. So we can say the torque about the pivot. We can write this torque about the pivot. First is our due to gravity. Let us call it as tau g. Then tau g will be equal to our mg times L sine of theta. Restoring, so we just put a negative sign, and this theta is very small, so we can write this as our mgl times theta. Now we come to our centrifugal force. And like I said that the pendulum is the bob is at a distance r, which is our L sine of theta, or we can say the centrifugal force, and in this case the bob is at r, which is our L sine of theta, or sine theta we can write this as L times theta from the axis of rotation, or we can say from rotation axis. And for rotation axis, we can find out that our centrifugal force, if that we can write as F cent, then F cent will be equal to over m omega square times r, or approximately we can substitute our r, we get this as m omega square L times theta. Now we come to the torque because of this centrifugal force. Therefore, we can say that the torque due to our centrifugal will be equal to our force centrifugal times our L, and this gives us m omega square L square times theta. And now we can use the equation of our motion. So we have our equation of motion, and this equation of motion, because of the rotational motion, rotational equation about the pivot. So we can say our pendulum's rotational equation about the pivot. And we can say that our net torque will be giving us our moment of inertia theta double derivative, and the moment of inertia of mass m at a distance L from the pivot, that's our I, will be equal to our ml square. So we get that our I is equal to ml square. So this will be ml square theta double derivative. And we have two forces. One is our gravitational force and other one is our centrifugal force. And we just found out that the torque because of both tau central and torque due to gravity. Therefore, we can say that the net torque that is our tau net will be equal to minus mg and minus mg L theta plus m omega square L square theta. So this is our net torque, and we can substitute the net torque in this equation. So we get this as our ml square theta double derivative is equal to minus mgl theta plus m square L square times theta. And from here we can just take out this m, and we can write this equation in the format of double derivative, and this will be equal to our we have here plus, okay, we can also cancel out our L. So this square goes by this L and this square goes away. Therefore, let me write it. This is our L is equal to, and we here have minus m. No, we don't have m. We have g theta, and this is a plus omega square L times theta, and we can also take this theta as common. Okay, now it's almost done. Therefore, we can say from here that our theta double derivative will be equal to, or we can take it in the right side, and this comes as our plus, we have this as g upon L minus omega square times theta is equal to 0. And now we can just make a comparison with double derivative omega square theta is equal to 0, which is a standard equation of our SHM. Therefore, from 1:1 comparison, we can say that for a small angle, we have our omega square is equal to g upon L minus of our omega square. Or we can just remove the square root. We get this omega is equal to g upon L minus omega square and its square root. So this is the angular frequency, small angular oscillations. And here we have to remember that the theta is very small, and second important part is that for physical oscillation to take place, the ratio of G upon L should be greater than our omega square. Okay, then only the term inside this square root will be positive. If it is on the other side, we can say that the pendulum will be not oscillating, it will be becoming some kind of unstable part. Okay. So this condition has to be satisfied for the oscillation to be taking place. And we come to the next question. And it states that a particle of mass 50 gram moves under a attractive central force with a magnitude of 4r raised to power, we can say 4r cube dynes. The particle has an angular momentum of 1000 gram per centimeter square per second. So based on this, we have 3 questions. Find the effective potential energy. On a sketch of effective potential indicates the total energy for a circular motion. If the radius of the particle's orbit varies between r0 and 2r0, determine the value of r0. Okay. So this is the basic question given to us. And we need not to worry so much about these units. We are just going to solve the question. And here we have to remember one important thing, that with the central force is given as our attractive force. This we have to remember. Okay. And because we have to find out the effective potential energy, and we know that the relationship between the force as well as its derivative, we already know that. Derivative of the potential energy we know. Okay, so we start from there only. So we have our part A, and this part A, we find out that the relation between force and potential energy. Relation between force and potential energy, and this force, which is dependent upon distance r, will be equal to minus the derivative of our potential energy, which is represented as our u. Therefore, we can say from here that our du will be equal to minus fr times dr, and we are given that f of r is equal to 4r cube. Okay. And this is attractive central force. Therefore, you can say that this is attractive. Therefore, we get that our f of r will be equal to minus 4 times r of cube. Okay. Now we can just substitute it. We get our derivative of u is equal to minus 4r cube, okay, times dr, and this gives us 4r cube times dr. And we simply integrate it. We get that our u of r will be equal to integration of 4r cube dr. So this will be coming as 4r4 upon 4, and 4 and 4 goes away. So this comes as our r4. So this is our potential energy at a distance r. And here we have to also remember that the effective potential energy, this is the potential energy because of the force that is acting on it, and it is you can say moving in a circle, So there will be a centrifugal term that will also contributing to this energy. So we can say that the effective potential energy, let us call this as our U effective of our R is equal to our U of R plus L square, and that is our 2m R square. Okay. And we simply substitute their values, and we get from here, we know that our L is given as our 1000, mass is 50 gram. So we get this as our U of R is equal to, this is U effective. U effective R, U of R is of R raised to power 4 plus, and L square will be our 1000 square divided by our 2mR divided by 100. So that will be giving us 10,000 divided by R square. Now we come to the total energy for our circular motion. So you can say total energy for circular motion and it is given in the question that it is radius is our RC. Therefore we can say that the centrifugal force is going to balance the central force. So you can say that circular motion for a radius RC, then we can say the centrifugal force balances central force. So we can write that our L m RC cube will be equal to our central force, which is 4 RC cube. Okay, because centrifugal force is our Lm upon R cube, and central force is this is attractive. Okay, so we can just solve it. From here we can get that our L square will be equal to 4 times m R C raised to power 6, and we simply substitute the values. We know, therefore we can say from here that our RC will be equal to L square, and we have this as 4m whole raised to power 1 by 6, and we are given L is our 1000. So we get this as our 10 raised to power 3 whole square divided by 4, and mass is given to us as a 50, and this comes as whole 1 by 6. So in the numerator we are going to get this as 10, and in the denominator we are going to get this as 200 raised to power, or let me keep it as it is, and this is about 200 whole raised to power 1 by 6, and this will be equal to 10 raised to power 6 means 10 raised to power 4, and 10 raised to power 4 divided by 2 will be equal to 5000, and whole raised to power 1 by 6. Therefore we get that our RC will be approximately equal to 4.11 centimeters. Therefore, total energy for circular motion, you can say total energy for circular motion, let us call this as our E, then this E will be equal to our U effective at a distance of our RC. So we can simply substitute, because we already calculated first part, that is our this equation. So here we simply substitute our R by RC, and later on we can put the value of our RC, and we get this as our RC whole raised to power 4, and we have this as 10,000 divided by RC square, and this is our 4.11. So we get this as 4.11 whole raised to power 4 plus 1000 and divided by our 4.11 whole raised to power square. So we can say our energy is approximately equal to 877 ergs. And for part B, they have asked to plot. We can plot the figure later on. So let us deal with the part C first. And so we have part C, and part C says that orbit varies from R0, between R0 and 2R0. Given that our orbit varies between R0 and 2R0. So therefore it means the minimum radius is our R0 and the maximum is our twice R0. So we can call this as R minimum, and we can call this as our R maximum. And formula for our energy we already know. So we can say that our energy E is equal to our U effective R is equal to R4 plus 10,000 divided by R square. So therefore, depending upon the minimum value of R and maximum value of R, we can just reformulate the equation. Therefore, we can say that at R is equal to R0, we get the total energy, which is our E, will be equal to our U effective of R0 is equal to R0 4,000 divided by R0 square. And similarly, at R is equal to twice R0, we can say that our energy is equal to U effective and twice R0, giving us twice R0 whole raised to power 4, 10,000 and twice R0 whole raised to power square. And we can little bit solve this part. So we will be getting this as our U effective of twice R0. This will be our 16 times R0 4 plus, and this will be coming as 4. So 10,000 divided by 4 will be equal to 2,500, and this is R0 square. Okay. And we know that the energy is conservation of energy basically. Therefore, we can equate them. So we can say our U effective at our R0 is equal to U effective and twice R0. Therefore, we get this as our R0 4 plus 10,000 R0 square is equal to 16 times R0 4 plus 2500 divided by R0 square. Now it is a simple calculation, and for that we can just write this as our, if we this is our 16R4, R0 4, and minus R0 4, and this will plus 2500 R0 square minus 1000 upon R0 square, and equal to 0. Therefore from here we get this as our 15 R0 4, this will be your minus, and we get this as R0 square, so this will be 1000 minus 2500, we will be getting this as our 7500 is equal to 0, and this can be further written as 15 R0 6 minus 7500 is equal to 0, and from here we get that our 15 we can take as common, so this will be our, one second, this is 75, and it will be coming as 5, so we can say our R0 raised to power 6 is equal to 500. So our R0 is equal to 6th root of 500, which will be approximately equal to 3.17 centimeters. So we got our R0, and accordingly we can also find out twice R0, that is 6 point something. Okay. Now we come to the part B, that was asked to plot the graph. So we have a part B, and for part B we can say that okay, for part B we are going to find out the graph which states that sketch the effective potential. Potential means a potential energy, indicate the total energy for a circular motion. Okay, so this is not much of a problem. We already know that we are going to plot the graph between energy as well as our distance, that is our R. Okay. So let us take a common axis, and we are going to plot this into two parts. First will be this is our radius, and this is our energy, and energy is in ergs, and similarly we are going to plot it for our another value of our R, but that R will be our dependent upon our R0 as well as our twice R0. Okay, so we have two curves to be plotted. Okay, and this we can just make an approximate analysis of that, and let us suppose we start with 0, so this is 1 2 3 4 5 6 and something like 7, and we already know that our this energy, we are having two components. One is dependent upon our R4 and other one is dependent upon our 10,000 raised to power divided by 2. So energy is dependent upon two parts. One is our R4 and another one is our 10,000 divided by our R2. So we are going to approximately plot these individually, and then we can make a approximate guess about this particular graph. So our this R4, we can just say that it will be somewhat, it will be rising like this, and this is our R4. Okay. And the second graph, that is our 10 raised power, this is 1000 divided by R square, and it will be coming downward like this, and it will be a asymptotic graph we are plotting, and therefore there is summation, that is a total energy, the summation of both, so it will be slightly skewed in this direction, and it will be try to follow like this, and somewhere here we are going to get this as minimum value of our energy. Okay. And this is our minimum value of energy, and that our value of R, we are going to call this as R minimum. Okay. Please remember, this is only the approximation. Exactly it will be a little bit difficult, requires lots of calculation. And the second part, we can just draw between our R0 as well as twice R0. We just draw this still will be energy, and radius is there, and the shape of the graph we already know, it is not going to change, and we are going to have this minimum value of R, so this is our R minimum, and we already know our R0 and twice R0, so our R0 is our 3.17. Okay, so we can say that our R0 will be 3.17, so it will be somewhere here, so this will be R0, and twice R0 will be close to our 6 point something, so it is going to go somewhere here, so this will be our twice R0. Okay. So these were the 4 questions, and so this completes the 4 questions. Thank you.